Okay. So now at least now we'll have a fresh video. Now, we'll let everybody know that so you might have seen this possibly in my labs. So when I was preparing the rest of the class meetings for Chapter 2, I went ahead and prepared the second test as well. So practice test 2 is out there for you to take a look at. So it just covers all of the Chapter 2 sections, so 2, 2, 3, 8, and 9. I've only covered the first 2 of those so far. 2.3 will be today. And then next week on the Wednesday, I'll finish the chapter by then, and there will be a review. So 8 problems in total. So take a shot at the practice test and see how that goes. Okay. Although you might want to wait a bit since you won't have seen all the material just yet, but you will soon. Okay. All right. Now. I got to get the right document open here. Ah, dang it! Sorry, I was in the wrong. I was in the folder for wrong class. Okay. Okay. So previously we've learned what the inverse of a matrix is, and also how to compute it. What we're going to look at today is basically ramifications of a matrix being invertible. If you know that a matrix is invertible, then what else does that tell you about the matrix or systems of equations involving that matrix? This centers on what's called in the textbook the invertible matrix theorem. And all this theorem is a series of statements, 12 statements in all, where that are all saying it's exactly the same thing. So if you have A being a square n by n matrix, so all of this talk today is only about square matrices. These statements are either all true or all false. So if you know that the matrix is invertible, you can reduce it to the identity matrix by row operations. It has a pivot position in every row and every column because the number of rows and columns is the same. Ax equals b always has a unique solution. As actually, I'm surprised the theorem doesn't say this. It's actually not just at least one solution. It's a solution that's unique. Ax equals 0 has only the trivial solution. The columns are linearly independent, and so on. So these give ways to determine more rapidly whether matrix has an inverse. Okay. So the problems, many of the problems that come from this section, you're given a matrix, and the goal is to determine as quickly as possible, with as little work as possible, whether the matrix has an inverse. And using certain statements from the invertible matrix theorem is how you can tell. So, for example, if you find that there's no way the matrix has a pivot position in every row, then you know right then and there it's not invertible, and so on. Okay. Now, this first matrix has an interesting structure to it. But notice that we look at the main diagonal here, where we have a 4, -3, -4. All the entries above that main diagonal are 0. So we have a name for that kind of matrix. It is called a lower triangular matrix. Now, we've seen the opposite of this before. Like if we take a square matrix and perform row operations to get it down to echelon form, that matrix is called upper triangular. So when you have a matrix that is triangular like this, whether it's lower or upper, so like if I take the transpose of this, and it would be upper triangular matrix, it's actually very easy to determine whether the matrix is invertible or not, because these entries on the diagonal, you can think of them as these would be your pivot positions. So now, if you did perform row operations on this matrix anyway, it won't be any need to do it. But let's suppose I wanted to eliminate these entries down here to make it to get echelon form. What would happen is, like, if I take a multiple of this row and subtract it from the second row and the third row, well, because there's zeros up above here, nothing else down over here would be affected. I eliminate these entries, nothing else here would be touched. Similarly, when I go to use the second row, the second row to get rid of this element down here, because there's a 0 over here, this -4 won't be touched. So what that means is, what do you have on a diagonal? Those are the pivots, the pivot positions. So what you'd find is because all of these entries that are on the diagonal are non-zero, then we know that the matrix has an inverse. So I'm going to make this more general statement. A triangular matrix. Come on. Okay. Any kind of triangular matrix, upper or lower, is invertible if and only if its diagonal entries, so the entries here along the main diagonal, are all non-zero. In fact, I can say something more. If I were to compute the inverse of this matrix, the diagonal entries in the inverse would be the reciprocals of whatever entries you have in a diagonal. So I know that the inverse would have diagonal entries 1/4, -1/3, -1/4. These other entries would take a little more work. So in fact, I can also make this statement. The inverse of a lower upper triangular matrix is lower upper triangular. In other words, taking the inverse preserves the triangularity. So whatever kind of triangularity you have in the original carries over to the inverse. Okay. All right, so here, if you see it's any kind of triangular matrix, just look at diagonal entries. If they're all non-zero, then you know it's invertible. And we can also say diagonal entries are the pivot positions. Okay. All right, so triangular matrices come up in quite a few applications when it comes to solving systems. They're definitely a lot more convenient to work with. So it's good to be aware of these properties of them. Okay. On to the next matrix. Very quick to tell that this matrix does not have an inverse. Because anytime a matrix has a square matrix has a column or a row that's entirely zeros, then that means that that's a row or column. It cannot have a pivot position, and an invertible matrix has to have a pivot position in every row, has to have one in every column. So this is a deal breaker. Similarly, if it's, this doesn't come up on the homework problems, but matrix with two identical rows or columns is not invertible because a row or column operation would cause that row or column to become all zeros. So really, this situation is essentially the same. You're just one row operation away from this, or column operation away from this. All right. So look for that row or column of all zeros. That's a quick deal breaker. Okay. Now, if there's nothing obvious like that, like so the first two problems, one could tell pretty quickly just by looking that the matrix is or is not invertible. But if that's not the case, then it's necessary to do some row operations, and that's what we have going on here. So the idea is to try to reduce it to at least echelon form and see if you can get a pivot position in every row. So first thing to do to make row operations more convenient, go ahead and swap the first and second rows. Whenever you have a 1 here in the first column, you like to move that to the first row. So, all right, so now I've carried out the swap, and now I just need to eliminate this entry down here. Okay, so now everything's eliminated down here, and we have these to contend with. Now, I will go a little further to perform one more row operation, but notice that the third row is a scalar multiple of the second row. So if I take the second row and multiply it by -3, I'm going to get exactly the third row. And anytime you have that happen, that means not invertible, because in that situation, if you were to continue with row operations, so I go ahead and perform the operation to eliminate this element, then we get a row of all zeros, and we see that it's not invertible for that reason. So the third row is not going to have a pivot position. So by the invertible matrix theorem, we have a deal breaker. It cannot be invertible. Now, a time-saving tip here is a square matrix is not invertible if any row or column is a scalar multiple of another. So I mentioned earlier that if you have two identical rows or two identical columns, then it's not invertible. This is a more general version of that. If you have two rows or two columns that are parallel to one another, so it's vectors, they have the same direction. Because then again, you're just one row or column operation away from getting a row or column as entirely zero. So once you get to this point, then you can bail out and say, okay, it's not invertible. Now this is a matrix here that has a somewhat similar appearance as the matrix from a previous problem, but at this point, there's no obvious criterion that leads to it concluding it is or isn't invertible. So once again, we're stuck with having to do row operations. So here, go ahead and eliminate this -4 at the bottom. Okay. And here too, it is possible to reach a quick verdict because we have, you look at these two rows here, 4, 2, and -3, -28. These two rows are definitely not scalar multiples of each other. They are not parallel. So in fact, you could conclude just from this, because you're almost to echelon form, that when you get down to these last two rows, if they're not parallel, and they're certainly not going to be parallel to any rows up above, then you know that it's going to be invertible. Now go ahead and perform the last row operation anyway. The numbers are not going to be so nice this time. We get a -53/2 there, but in any case, because it's non-zero, we do have a pivot position in every row. So we're done with that. We know that it is invertible. All right. This matrix right here, it's actually possible to reach a very quick verdict. Can anyone tell me, based on things I've said earlier today, how you can quickly determine the invertibility or lack thereof of this matrix? What kind of matrix is it?
It's upper triangular.
It is upper triangular. So is it invertible?
Yes.
Yes. Why?
Because it has all the pivot points on all the rows and columns.
Yeah. So equivalently, we have these 4 non-zero diagonal entries, and yes, these are the pivot positions. So so right away, you can make that conclusion that it is invertible. Yeah, so look for triangularity, look for other clues like parallel rows or columns, 0 rows or columns, things like that. If none of those apply, then you're looking at row operations, and you may not have to go all the way to echelon form. You might be able to tell beforehand that yes, it's invertible, or no, it's not. I found it generally easier to rule out invertibility than to show that it is the case. All right, this last one deals with linear transformations. Now, a linear transformation essentially amounts to matrix vector multiplication. And before, we've seen the standard matrix of a linear transformation. So applying a linear transformation like T to a vector like x1, x2 is equivalent to multiplying by a standard matrix. So we want to show that this linear transformation right here is invertible and figure out what the T inverse is. And we can do all that by working with its standard matrix. So how do we know if linear transformation is invertible? Well, we can get a standard matrix from a formula here. And if that matrix is invertible, then its inverse is a standard matrix of the inverse transformation. And we can use that to figure out a formula for the inverse, just like this one. So really, everything revolves around the standard matrix and its inverse. So we need the standard matrix of its transformation. So all we have to do is look at the coefficients of x1 and x2 in these formulas, and that will give us the standard matrix. It's going from R2 to R2, so 2 inputs, 2 outputs. So it'll be just a 2 by 2 matrix. So you see the coefficients of a first output go here, coefficients of a second output go here. So we just need to know, is this matrix invertible? Now, for a 2 by 2 matrix especially, it's pretty easy to tell. Like if the 2 rows are not parallel, or the 2 columns are not parallel to one another, then you know it has an inverse. Another way that's easy for 2 by 2 in particular is look at what's called the determinant. Now, determinants are something that we will be looking at much more closely later on, but at least for a 2 by 2 case, the definition is you just multiply the diagonal entries, A11, A22, and then subtract the product of the off-diagonal entries, so minus A12, A21. So multiply, and then subtract this product here. So this times this minus this times this, which you may have seen in other classes, like if you've taken differential equations, you deal with a Wronskian, and that is a determinant also. So we would have done that in some 2 by 2 cases. Later on, we'll learn how to compute determinants of larger matrices than this. But for now, we're content with 2 by 2. So if a determinant is non-zero, then the matrix is invertible. So we can go ahead and do that in this case and compute the determinant. So this times this, so 18 minus 2 times minus 5, and we get a result of 8. So that means that this matrix does have an inverse. Therefore, the transformation T also has an inverse. Getting the inverse in this case doesn't take too much work because it's a 2 by 2 matrix. So if I recall the formula for the inverse of a general 2 by 2 matrix, which is one of those good to know things, where you swap the diagonal entries, you negate the off diagonal entries, and you have to remember to divide by the determinant. So in that case, we can just apply this formula to this matrix to get its inverse. So that's carried out here. So here I've done this swapping and negating as needed. Then I'll just go ahead and distribute the 1 over the determinant through that. And so here, these are the coefficients of x1 and x2 in the inverse. So if I want to write down a formula for the inverse of the linear transformation, so here we have coefficients of x1 and x2 for the first output. The second row are the coefficients of x1 and x2 for the second output. And this is the formula for your inverse. So what that means is if you were to take given x1 and x2 and substitute them into the formula for the original transformation, get these outputs, and then substitute these into this transformation for x1 and x2, what will happen is you wind up with the original x1 and x2 that you started with, that t inverse and t, when composed together like that, will cancel each other out. All right, so if you want to know if a linear transformation is invertible and to get its inverse, that just means working with the standard matrix and getting its inverse after checking that it exists. All right, so other questions about this problem or what's happened in the previous problems?
Can the determinant be negative as well?
Yes, the determinant can be any real number.
All right.
But as long as it's non-zero, the matrix is invertible. In fact, if I were to swap the rows or swap the columns of this matrix, that would negate the determinant.
Okay, thank you.
Other questions? Now you'll see this anyway when you look at the practice test. That I only chose. Since there's eight problems encompassing the whole chapter, the only one I chose from this section is a problem like this one, where you're working with the inverse of a given linear transformation. Any other questions about this section? Well, this is a fairly quick one today. So I'll go ahead and stop recording here. Anyone has any individual questions can stick around, and everyone else can scram.